Welcome to the lecture on analog microelectronic circuits. This is lecture 3, and we started unit 2, and in unit 2 we are uh, discussing about bipolar junction transistor, which is one another 3-terminal device. Right. So in the previous classes, I hope you remember, we started with bipolar junction transistor. We just looked at the history. Then we came to the device structure and understood the 4 different ways I can bias BJT. And followed by, we have looked at DC numericals. And then in yesterday's class, we understood the operation of transistor. The operation is the all the 3 regions, emitter, base, and collector, are doped selectively. Selectively in the sense, emitter is doped very heavily, base is doped very lightly, and collector is doped moderately. And this is maintained in order to ensure the proper operation of the device. So under this case, and we discussed the active mode of operation of an NPN transistor, because that is the mode which we use for amplification. Now, if you look at the emitter base junction, when it is forward biased, emitter will be, since it is heavily doped, it will actually having lot of electrons which will come to the base. But since base is very thin and lightly doped, few of the electrons will get recombined, but the rest of the electrons will be heavily attracted by the reverse bias potential which is available at the collector. So that results in a current, that results in an electron flow from emitter through base to collector. But one thing is sure, that the emitter current or the number of electrons originated from emitter is not reaching collector, because few of the electrons are actually getting recombined in the base region. But still, majority of the electrons are collected by the collector, and that constitutes a collector current. Since electrons are flowing in this direction, we have seen that the current will be actually flowing in the opposite direction. So collector current will be in this form. Then yeah, because of the movement of holes here, there will be a base current, and these two will be constituting the emitter current here. So with that understanding, and with the help of device physics, we have developed the equation. So we have written collector current. Collector current is actually as a result of the electrons that is flowing from the emitter region because of the emitter base forward bias junction. So we applied the same diode equation here and extended to this collector current, and we got collector current as Is into e to the power of Vb by Vt. Or if you write very precisely, it is, the equation is of this form, but we neglected this one because this saturation current is very small. So we neglected that, and we wrote Ic as this. Then we also wrote the relation, or the, by applying KCL, the sum of the currents, the sum of entering and leaving currents should be same. With that, we understood that the emitter current is a sum of base and collector. And with that, we wrote other relations, and we also brought in alpha and beta, which are defined as a current gain in BJT. So with that, we just looked at the structure, the cross section of BJT, and understood that it is not a symmetrical device. And then later we looked at the symbol and had one comparison between MOSFET and BJT, where MOSFET had a very high infinite input impedance, where BJT's input impedance is a finite value. We looked at 3 configurations and had solved few numericals. So today we'll continue that. So while continuing, we'll start with the current equation. So we'll try to understand the current equation, and we'll write the relations in current equation, and then we'll proceed. And the way we study BJT will be same as MOSFET. So every point you can have a comparison with the MOSFET and get things right. Today we'll be writing current equation. We'll look at a very generic model. Then we'll go for small signal parameters. And if time permits, we'll start with the small signal models also. Right. All right. So I'll just summarize the current equations once again, because based on this only we will progress in our studies. So we know that collector current Ic is Is into e to the power of VBE by Vt, where Vb is the forward voltage at the emitter base junction, and Is is the reverse saturation current, and Vt is the volt equivalent of temperature. And Emitter current can be written as the sum of collector current and base current, and collector current is beta times IB, and emitter current is beta plus 1 times IB. These two relations also we have seen. So with that, I can write base current can be written as collector current by beta. So that means I can write base current as, since collector current is this, base current is Is by beta into e to the power of VBE by VT, and IE can be written as IE and IC. All right, yeah, IE can be written as it is beta plus 1 divided by beta into Is into e to the power of VBE by VT. Right. So we know what is IC. So with that, I substituted for even for IE also. So now if we look at these three equations, it is very clear. We can write the current equations in a BJT for collector, base as well as emitter in this form. Now, if you closely look at this current equation, for example, if you look at this collector current equation, we will actually observe a very interesting property of BJT. If you look at this equation, you will, so if I rewrite this equation again, IC can be written as Is into e to the power of VBE by VT. So by looking at this expression, can you comment or what is your observation? So collector current depends on what? What dependency can we observe here? So we can see that the collector current IC, it does not depend on, IC does not depend on collector voltage, right? So your collector current is not depending on collector voltage. So this is true when your device is in active region. So when your device is in active region, collector current does not depend on collector voltage, but on what? It depends only on the base emitter voltage, or I can say for a fixed VBE, for a fixed base to emitter voltage, the device is in fact drawing a very constant current. Device draws a constant current. Can you observe that? So if you look at this current equation, collector current is constant, or collector current is equal to Is into e to the power of VB by VT. In that only variable is VBE, and now if your VB is constant, your collector current also will be constant, right? So whenever a device is providing a constant current, I can say that it can act as a current source. So BJT also act as a current source. So how can I understand that? Say you have a BJT. This is connected to some voltage. Now, if you are providing a appropriate VBE, say I am providing a voltage, say Vx, I am providing a voltage Vx, which is equal to VBE. Now, I can write the collector current as the function of only Vx. So now, if your Vx is constant, your current will be constant. So this is equal to, or this is equivalent to a current source or a constant current source, right? So what is the specialty of a current source? A current source will actually provide a constant current irrespective of the voltage across it. Now this is actually your collector current, and the voltage across the current source is actually VCE, and from the relation we understand that even though VCE varies, in as soon as the BJT is an active region of operation, even though your VCE varies, your IC is not going to vary, right? Or if I try to draw a graph between VCE and IC, I can say that your VCE, as long as your VCE, as long as your VBE is constant. So now your VB is somewhere around, say for example, VBE. So you have provided V1 as the VB. Now that will actually give you a current of Is into e to the power of Vx by Vt, which will be constant, right? So irrespective of Vc, so your collector current is not depending on collector to emitter voltage. Whatever is the collector voltage, collector to emitter voltage, your transistor will in fact provide a constant current. So in that way, I can say BJT also act as a constant current source. So as soon as I identify that a device can be operating when the device acts as a constant current source, I can use that as an amplifier. Yes. So I saw the responses just now. Yes, it depends on temperature. It's very important to note that it depends on temperature, and we will use that for some other reason. Yes, it depends on emitter to base voltage, IS and temperature. Yes, those are the dependencies. Yes, thank you for the response, Kirtana, Manikandan and Manjunath. So the point I want to focus here is the interesting property of BJT is collector current is not depending on collector to emitter voltage, and for that matter, the BJT act as a current source or a constant current source. Now, if a device is operating as a constant current source, I can use that device for amplification purpose. Probably I am telling this from MOSFET and I did not explain in that way. I hope you would have understood why a device operating as a constant current source can act as an amplifier. Say for example, so this is true for both BJT and MOSFET. Say I have a dependent current source. We have seen that even in the initial classes. Say I have a dependent current source. Say now this voltage is actually V in, and now this current source is having some value. Say the current source value is I. Now that I depends on this V in. So I is actually say K into V in, right? That means you have a device with you, and the device in fact is behaving as a voltage dependent current source, voltage dependent current source. So this there is a current source, a controlled current source here, and this current source depends on voltage V in. Now, how can I say that I can use this as an amplifier? Say for example, I am connecting a load here. I'm connecting a load device, say RL here, and I'm taking voltage across this. So I can write V out as minus K into V in into RL, right? So if I write AV is actually equal to minus K into RL, right? So your voltage gain of this circuit, or you can see that your input is actually amplified by K times, which is actually the property of the device, and by the RL or the load resistance. So whatever resistance I connect here, appropriately I'm actually getting the gain value, right? So gain can be adjusted by actually putting this resistance value RL. Now this is actually the case of a MOSFET. Now the difference is, I understand that there will be actually a finite resistance in the case of BJT. Say for example, if there is a resistance also, this holds good, right? This relation actually holds good because the voltage, so now this is V in, so the voltage across this is V in. In fact, it is V in. So the same output I will be getting at the at V out also. It doesn't matter. Depends on input resistance, or the resistance between those two terminals is not actually affecting the voltage gain. That is what we can see here, right? So I hope this is clear, because from BJT MOSFET onwards, I am telling if a device is operating as a constant current source, it can be utilized as an amplifier, and this is how it can be used as an amplifier. Is there any doubts in this? Whatever I explained just now. All right. I hope you understand this. What I did now. Okay, so coming back, so I understood that BJT is also operating as a constant current source, and for that matter, I can use BJT as an amplifier, right? Now, uh, before moving further, before going to discuss any other things, I just want to uh, familiarize with you a model of a BJT. So in active mode, so everything what we do here will be in comparison with MOSFET. So if you remember in MOSFET, we understood that the transistor is holding a constant current in saturation region, and we have obtained the model for transistor MOSFET in saturation region. Similarly, here we will write the model of transistor BJT in active region of operation. Right, that is what we are going to do now. Okay, so I'll not call this as a small signal model, rather this is actually a very generic model, and often we call this as a large signal model. For the matter, we can use this for, this is the representation of BJT at any time in active region of operation. So say your BJT is in active mode. Now we know that say this is your BJT. In active mode means this is base, this is collector, this is emitter, and this will be forward bias. So this is NPN. So this is forward bias. So this should be plus minus, and this is reverse biased. So this also should be yeah, this should be plus with respect to base, right? With respect to base, that should be plus minus. Now with the understanding what we developed so far, can you just tell me if I try to draw a model for BJT, considering this as the base, this as the collector, and this as the emitter terminal. So how can I model, or how can I represent BJT using some model? So basically, why do we need models? Models are required to understand the operation, and we can actually, your analysis will become very, very easy if you can represent a device in terms of some known elements, rather instead of treating it as a symbol with two junctions. If I can get the behavior of the device in terms of some known elements, that will be very, very good, right? So okay, let me just check with uh, yeah, Anushka, are you there?
Yes, sir.
Yes, Anushka, are you following what we are doing in today's class?
Yes, sir.
Yeah, so from the previous class and today's class, we understood the operation of BJT, right? To some extent, we understood that. Now, if I want to represent BJT using a model in terms of some known elements, how can we represent? So if you look back with MOSFET, we know that MOSFET had a gate. So this is in, let me just write it here. This is gate, this is source, and this is drain. So whatever I have written in blue is for the MOSFET terminals. And I understand gate is isolated from the rest of the device. So there is no physical connection between those two. So whenever I say that there is no physical connection between those two, that is how we represented MOSFET model, right? Now,
Yes.
what is the case of BJT? From the discussion so far, what do you think? How can I best represent a model?
Something so that we can have a constant current.
Yes, very good. So where can I do that? Where can I connect that? From this discussion, we understand that transistor is carrying a constant current. The current is IC. So can I represent between
Yes.
collector and emitter it as a constant current?
Yes, sir.
All right. Okay. Now I will use this dependent current source symbol itself. And what is this current? This current is actually Is into e to the power of VBE
Minus.
by Vt. VBE by Vt. So far I am not representing the small signal model. I will talk about small signal model little late. Now this is a generic model. So that I understand. Now, so now how can I best represent the emitter based junction? What is an emitter based junction now? Emitter based junction is a
Emitter base junction is forward bias, sir.
very good. It is a diode, right? So thank you. It is a forward bias diode. So I will represent that. using a diode here, right? So this is actually the VB voltage, and this also will actually but there is a current flow even here. So this current, I know what is this current. Now can you tell me what will be this current?
Current, no.
This should be base current, right?
Yeah.
If I know collector current, I can write base current as Is by beta into e to the power of Vb by Vt. Is it okay?
Yes, sir.
The sum of these two will give you emitter current, which is beta plus 1 divided by beta into Is in e to the power of Vb by Vt. Right. Is that okay?
Yes, sir.
Thank you, Anushka. Yes. So I hope others also understood what we have done here. The best way what we can model MOSFET is like this. So just to have a completion on what we have done, so I'll just draw the symbol over here. So this is actually the emitter, and now this is the collector point, right? So this is how we understand the model of the bipolar junction transistor in active mode. So this is actually BJT model in active region. In fact, this model is called as large signal model because this holds even good within the active region when even if you apply a large voltage difference also. So whenever we whatever we call as small signal model is actually the model for a transistor when you apply incremental change or very small change in the terminal voltages. Now this is the model which holds good even if you do a large change. When you say large change, it is not in terms of kilovolts or something. It is again in terms of few volts only. But if the transistor is operating within the active mode, then this model holds good, right? Uh, so if so far if you have doubts, we can have a discussion now before we proceed further. Any questions? Now, if you look at the model, you can observe that the one difference is in BJT, sorry, in MOSFET, we left the gate source voltage as open, right? Because there is no current flow. But in this case, it is not. It is not like that. There is a current flow. That is why you have a forward bias PN junction. Any other questions? Okay, so if not, we will proceed further. If you have questions, we can take it at the end also. Now, so moving on, let me start with the small signal operation here. Right. So to study that, I'll just take a very simple circuit. Right. This is VCC, say this is RC, uh, this is voltage between collector and emitter, and say I'm actually connecting a signal here. Now we know that signal cannot directly bias the device, so we have to actually provide a DC voltage also. So DC voltage I'll mark it as VBE, and if it is a signal voltage I'll mark it as small VBE. So in fact I have a composite voltage here, I mark it as small v capital BE, right? Now since the now the device is in presence of DC and AC, I can mark all the currents here as a composite current. So the base current will be flowing in this direction. So I'll mark it as I capital B. Collector current will be in this way. It is I capital C, and emitter current will be here. It is I capital E. And this voltage also I can mark it as VCE. Right. Now, I hope that this is a very simple circuit. I have just used a resistance RC. That's all. Right. So probably I'll just mark it as okay. That is some node. Leave it. Now, so now if I look at only the DC picture, if I want to see only the DC picture of this, so what is the DC picture? I no need to consider the small signal. So the circuit will be something like this. We have a VBE voltage here. That's all. So that will actually give you a current DC current IB. Now here will be your VC DC voltage that is established through VCC and this RC, and this will be the collector current IC, and the total emitter current will be flowing here, right? So the relations we know, so far we know the relations, and VB we are directly giving, and VC, the voltage here is established as, so what is this voltage VC? VC is actually VCC minus IC into RC. These are the DC conditions, right? Now, so for AC, or if you look back at this this picture, the circuit which is having AC voltage, what I understand is there is a DC voltage VBE. On that DC voltage, I am actually applying a small signal which is small VBE, and in together I have a composite signal VBE, which is a sum of small VBE and DC voltage VBE. Right. So with this we'll just analyze further, and since we know that this is a composite signal, so this is composite, and this is AC, and this is the DC voltage. Now, now let me write the current here. So now if I write the current here, current is collector current. It is a composite current. So I'll write IC, which is equal to IS into e to the power of voltage is VBE, but now that voltage is actually a composite voltage VBE by VT. VT, right? Or if I write this further, I can write IC is equal to IS into, I can substitute for VBE, which is DC voltage VBE plus small voltage, small signal voltage VBE divided by VT. Or I can write this further as IS into e to the power of VBE by VT into e to the power of small VBE by VT, right? So can you tell me what is this component here? What is this component? IS into e to the power of VBE by VT. What is that? Any response? Can I get some response in the chat box? Yes, it is IC. Yes, very good. So it is IC. There is a DC current IC. So I can write IC equal to, let me use the same color here. IC equal to IC into e to the power of VBE divided by VT. Right. Now we know that the VB voltage, so the voltage which we applied here, small VB, is a small signal voltage. So if VBE is small signal, if VBE is small signal, right, how can I approximate this e to the power of e to the power of x, where x is very small? So how can I approximate that? Yes, I'm seeing the responses from everyone where you have written it as IC. Yes, Kirtana, it is true. So now, when you have something called as e to the power of x, and when your x is very small, when your x is small, I can approximate this as 1 plus x, right? So I'll do the same thing here. I can write IC as capital IC, sorry, which is a DC voltage into 1 plus VBE divided by VT. So with understanding that VB is a very small signal, approximately it is few millivolts, right? So how will I write this further? I can write IC as capital IC plus capital IC by VT into VBE, which is a very important relation. So what I have written here, I have IC is actually the composite current is equal to the DC component, the DC current plus what should be the other component? This component is actually AC, this component is AC, right? So from this if I so I know that I capital C is equal to IC plus IC by VT into small VB. That is the expression what I have written just now. Now, if I look at only this component is actually AC current. So I can write AC current IC as IC by VT into small VBE, where this IC by VT is so what can be IC by VT? What units it will be having? It is current by voltage. IC by VT, it is actually conductance. Yes, very good. It is conductance, and this IC by VT is actually defined as the figure of merit or the conductance, and we call it as GM, the mutual conductance or the trans conductance of a BJT. IC by VT is GM. So I can now write IC is equal to GM into VBE. And now if you want to compare with the drain current or the MOSFET current, in MOSFET we wrote that the MOSFET current was ID equal to GM into VGS. It is very similar to that. So the AC collector current is equal to GM into VB is the is an important relation, right? So how to understand this? How to understand this further? Let me look at the characteristics of. Let me look at the CARA. So VBE, this is the composite voltage VB, and this is the composite collector current IC, right? Now, if you look at this SCARA, we will understand that till the cut in voltage there will not be any current because it is a forward bias PN junction, but after that you will have a current. Now say you have biased your BJT at a particular VBE voltage, that is a DC VBE, and on that if you are providing actually a small signal there, now the corresponding, so your DC VB will in fact set a DC collector current where you will have an IC. Now the varying small voltage also will actually in fact provide a varying collector current, which is not drawn properly. I haven't drawn it properly. So yeah, it will be in fact it will be symmetrical in that sense. So what I have here is what I'll have here is actually a larger variation. A small variation in the base to emitter voltage is in fact giving you a larger variation because the CARA looks like an exponential curve, and that will in fact give you a larger current on this side, right? So is this clear? Is this clear? The way I developed or I wrote the relation between small signal current and small signal voltages. Any doubts so far? All right, let me quickly finish a few more things. Uh, let me just define the other currents, and so base current and resistance seen at base, resistance at base. So these whatever I am doing now is very important when we actually draw the small signal. So I know that base current IB can be written as IC by beta, right? Or this can be further written as IC plus IC by Vt into Vb, which is that is what we have written just now, right? So your IC is IC plus IC by Vt into Vb. So that the same thing I am writing here into 1 by beta, right? Now IB is actually the DC base current and the AC base current. Now, so DC base current is related as IC by beta. So how the AC base current will be? So IB is equal to IC by Vt into VBE divided by beta, right? Or this IC by Vt, we know that it is GM. So I can write this as IB is equal to GM by beta into VBE. This is the relation between the base current and the relation between the base current and base emitter voltage. Right. So say if you have this BJT here, now the AC current is VBE in this form, and that will in turn give a AC voltage is VBE and base current will be in this form. Now if I look at the base terminal, so if you compare to MOSFET, looking at gate, the gate current was 0, and for that matter the gate the input resistance seen at the gate was infinity. But now since gate current is there, you can definitely see a small signal resistance at base. The small signal input resistance can be obtained here, that is between base and emitter, and looking into base. So if I look from look into base, I can in fact obtain a finite resistance looking into base. That is what we even mentioned in the beginning. So how will I get that? That resistance is in fact VB by IB. That will be VB by IB. So VB by IB from the previous relation is beta by GM. Now we need to represent this as a resistance. We know this will be definitely a resistance value, and that is usually denoted as a resistance called as R pi. So this beta by GM is nothing but R pi. Or to have a better picture, R pi, how we write R pi? It is beta by GM. Now what is beta? The relation what we can write. So now this R pi is a small signal parameter, and this small signal parameter will be depending on DC voltages or DC parameters. Now what is beta? Beta is in fact IC by IB. That is beta. What is GM? GM is IC by VT. This is the relation, right? So if I solve this further, I will get to know that VT is sorry, R pi is VT by IB. Right? Is it clear? So what I did now is in contrast to MOSFET, in MOSFET the input current or the gate current was 0, but now that is not the case. Since there is a base current, I have just written the base current, and from base resistance I also wrote the input resistance at base. This is input resistance at base, right? So we'll discuss on this. Before that, let me just write about emitter current also. So emitter current. So these things are new because in MOSFET there is only one current which flows between drain to source. Now in the case of BJT, you have actually collector current, base current and emitter current. That is why these additional things we have to look at. So emitter current and input resistance at emitter. So how to look at this? We know that emitter current, this is composite current, is collector current by, I can write it as alpha, right? That alpha relation I can bring in here, that is IC by alpha plus small ic by alpha. Now emitter current, the composite current is the sum of DC current plus AC current small ie. Small ie is in fact small ic by alpha. So small ie can be written as small ic is ic by Vt into VBE, that is small ic. So this divided by alpha will give you IE, right? or I can write here IE is equal to, what is IC by alpha? IC by alpha is capital IE, right? So this is IE divided by VT into VBE, right? Now I can write this VBE by IE as VT by DC current IE. That can be written as RE, which is the resistance, the small signal resistance. So to picturize that, this is emitter current IE and this is say VBE. Now if I look into this terminal, the resistance seen is small re. What is small re? Small re is Vt by IE. There are very minute differences between these things because the previously R pi is Vt by IB, where your Re is Vt by IE, right? So writing this further, I'll just summarize. So far we have written three small signal parameters. One is GM. GM is IC by VT. That is the first thing. Second thing is R pi. R pi is VT by IB. And third is RE, where RE is VT by IE. Right. So any doubts so far? So we have looked at many relations today. So let me bring in the relation between this R pi and RE also, relation between R pi and RE. So we know that small VBE is R pi into IB, right? Small VBE is equal to IB into R pi, and VB can be also written as IE into RE. So that means IB into R pi is equal to, can be written as IE into RE, or this IB into R pi can be written as beta plus 1 into IB into RE, or I can say R pi is equal to beta plus 1 into RE. This is one more relation. So just to clarify that, so when you have current as IB and this as VBE, the resistance looking into base, the resistance looking into base is R pi. The resistance looking into base is R pi. At the same time, when you have a transistor, and if you look from emitter, the resistance seen is Re, and both are related as R pi is equal to beta plus 1 into Re. All right, so here I'll stop and we'll continue next day. So before that, I can take questions here so that I can clarify if you have doubts.